The space between the stars is not empty. It is filled with a ghostly substance astronomers call the interstellar medium, a cosmic fog holding the universe's deepest secrets. Within this vast, invisible sea, stars are born from collapsing clouds of gas and dust, and the very ingredients for life are forged. Yet for all we know, this medium remains one of the greatest frontiers of modern astronomy, teeming with questions that challenge our understanding of reality. By the end of this exploration, you will have journeyed through 25 of its most profound mysteries, from the invisible fuel of galaxies to the strange chemistry that might seed alien worlds. How can a cloud of gas remember a supernova explosion from millions of years ago? And what are the mysterious fingerprints written in pure starlight that we still cannot read? The answers lie hidden in the void. What do you think is the most surprising thing that could be floating out there, unseen? Our first mystery is hiding in plain sight, or more accurately, in plain darkness. It is the most abundant molecule in the entire universe, and yet we cannot see it directly. This is the enigma of molecular hydrogen. Think of it as the universe's primary construction material, the raw lumber and bricks from which every star is built. Yet to our most powerful optical and even many infrared telescopes, this fundamental substance is utterly invisible. How can we study something we cannot see? Astronomers became cosmic detectives, learning to track the suspect by its shadow. They discovered that in the frigid, dense nurseries where stars are born, molecular hydrogen is almost always found in the company of other, rarer molecules. One of these is carbon monoxide. While hydrogen itself is shy and gives off no easy signal, carbon monoxide is a chatterbox, emitting a clear radio whisper that our giant dish antennas, like the Atacama Large Millimeter Array, can easily hear. So, we listen for the companion to map the presence of the star fuel itself. It is a brilliant workaround, but it is also a profound limitation. What if there are vast reservoirs of pure molecular hydrogen floating out there with no carbon monoxide to betray its location? Our galactic maps of star-forming material might be incomplete, missing entire chapters of the story. This dark gas could be lurking anywhere, silently pooling, waiting for the trigger to collapse into a new sun. The very foundation of star birth, the most common molecule in existence, remains a ghost in the cosmic machine. Its full shape and distribution one of the interstellar medium's most fundamental secrets. If hydrogen is the universe's invisible lumber, then the second mystery is the fully furnished house that somehow appears in the middle of the construction site. Astronomers have found, floating within those same cold, dark clouds, a bewildering array of complex organic molecules. We are not talking about simple atoms here. We are talking about the chemical building blocks for life itself. Sugars, alcohols, and even the components of amino acids have all been detected in the vast molecular clouds where stars and planets are being born. This discovery shatters our old assumptions. Space is not a sterile void. It is a cosmic chemistry lab, and a surprisingly sophisticated one at that. The environment out there is brutally harsh. Temperatures hover just a few degrees above absolute zero. The density is a vacuum far more perfect than anything we can create on Earth. And yet, against all odds, these complex molecules are assembling themselves on the surfaces of tiny dust grains. Think of a dust grain as a microscopic workshop floating in an endless frozen night. Individual atoms like carbon, oxygen, and hydrogen drift through the void and stick to this tiny, icy surface. Once there, shielded just slightly from destructive radiation, they can shuffle around and link up. It is a slow, patient dance over millions of years, building molecule by molecule from the bottom up. The proof came from telescopes like the Atacama Large Millimeter Array, or ALMA. Perched high in the Chilean desert, ALMA dishes act as a single, giant ear tuned to the universe's faintest whispers. In a star-forming region nearly 400 light-years away, it detected the unmistakable radio signature of a sugar molecule called glycolaldehyde. This is not table sugar, but it is a key ingredient in the process that creates ribose, a fundamental part of the backbone of DNA and RNA. The implication is staggering. The very chemistry that could one day lead to life is not a rare planetary accident. It is a universal process written into the recipe of star formation itself. Before a planet even finishes forming, before its oceans pool or its atmosphere settles, the raw ingredients for biology are already raining down upon it from the surrounding cloud. This means the seeds of life might be a standard feature of newborn worlds across the galaxy, delivered from the interstellar medium like a cosmic care package. The mystery is no longer whether the ingredients are out there, but how this delicate chemistry survives the violent birth of a star and finds its way to a waiting, watery world. But if the seeds of life are being sown in those dark clouds, the light traveling from distant stars carries a different kind of signature, one written in a code we have yet to fully crack. For over a century, astronomers have been collecting a strange set of cosmic fingerprints. When starlight passes through the diffuse gas and dust between the stars, it does not emerge unscathed. Specific colors or wavelengths of that light are subtly absorbed, leaving dark bands in the rainbow-like spectrum of the star. We have catalogued hundreds of these dark lines, known as the diffuse interstellar bands. Each one is a clue, a unique signature of a specific molecule or atom that the light encountered on its long journey. The problem is, we have the fingerprints, but we do not know whose hands they belong to. We cannot match them to any known substance in our laboratories here on Earth. This makes them one of the longest-running unsolved mysteries in all of astrophysics. The leading suspects are large, complex molecules based on chains or cages of carbon atoms. Think of them as soot from cosmic fires, but soot of a very special kind. One strong candidate is a class of molecules called polycyclic aromatic hydrocarbons, or PAH. These are flat, plate-like molecules made of interlocking rings of carbon and hydrogen, essentially tiny fragments of graphite. Another fascinating possibility are fullerenes, soccer ball-shaped cages of carbon atoms, the most famous being Buckminster fullerene, with 60 carbon atoms arranged in a perfect sphere. These are not just theoretical. We have found evidence of fullerenes in space, and PAHs are strongly suspected to be everywhere. Yet, none of their laboratory fingerprints perfectly match the full, confusing forest of dark bands we see in starlight. The challenge is immense. These molecules are floating alone in the void, not in a test tube. Their behavior in the extreme cold and vacuum of space, how they vibrate and absorb light, can be subtly different from how they act on Earth. So the hunt continues. Every new observation with powerful telescopes like the Very Large Telescope adds more data, more mysterious lines to the catalogue. It is a cosmic detective story where the clues are written in pure light, and the culprit is a form of matter so widespread it paints the galaxy, yet remains frustratingly, beautifully anonymous. These mysterious fingerprints in starlight point toward complex carbon, but the center of our own galaxy reveals a mystery of pure, raw power. Rising from the heart of the Milky Way, like two colossal ghosts, are the galactic center lobe structures. These are titanic bubbles of radio emission, each one towering over 20,000 light-years tall. They dwarf everything else in the galactic neighborhood, stretching far above and below the flat plane of stars we call home. To picture their scale, if you could see them in the night sky, they would span an area over 60 times wider than the full moon. Yet they are invisible to our eyes, only revealing themselves as a faint hiss of radio waves. Their very existence is a screaming question. What cataclysm, what unimaginable release of energy could have blown these bubbles into the thin gas that surrounds our galaxy? The leading suspects are two of the most violent events the universe can produce. The first is a starburst, a frenzy of star formation so intense it becomes self-destructive. If millions of stars were born in a short, fiery burst at the galactic center, their combined stellar winds and subsequent supernova explosions could have acted like a cosmic bellows, inflating these giant structures over millions of years. The second suspect is our galaxy's own supermassive black hole, Sagittarius, a star. While it is quiet now, it may have had a violent past, a past where it devoured a huge amount of material and then, in a fit of indigestion, blasted out a pair of jets or a spherical shockwave of incredible force. This eruption would have punched through the interstellar medium, carving out these lobes. Fascinatingly, these radio lobes have cousins seen in a much more energetic light. Nestled inside them are the Fermi bubbles, detected by a space telescope in gamma rays, the highest energy form of light. This suggests the event that created them was not a single, simple explosion, but a long, complex outburst that accelerated particles to near light speed. Visualizing this makes the mystery even more profound. Imagine an animation of our spiral galaxy, a beautiful pinwheel of stars. Then, from its very core, see two vast, faint bubbles slowly inflating, pushing outward, distorting the thin galactic atmosphere. They are a fossil record of a galactic-scale temper tantrum that happened millions of years ago. We are living in the quiet aftermath, staring up at the fading scars and wondering what exactly happened in our galactic backyard to leave a mark of such staggering, silent violence. These colossal scars from a galactic eruption are not the only strange structures haunting our skies. Far above the familiar plane of the Milky Way, astronomers have found something else entirely: clouds of pure hydrogen gas moving at impossible speeds. They are called high-velocity clouds, and their very motion defies the graceful, predictable rotation of our galaxy. Picture a spiral galaxy like a vast, slow-turning carousel. Most of its gas and stars move together in this orderly dance. Now imagine a handful of leaves caught in a hurricane, blasting across the carousel at a wild, perpendicular angle. That is what these clouds are doing. They are not following the rules. One of the most famous is the Smith cloud, a colossal streamer of hydrogen over 11,000 light-years long and 2,500 light-years wide. It is hurtling toward the disk of our galaxy at nearly 200 miles per second, and in perhaps 30 million years, it will crash into the spiral arm we call home. Where did it come from? That is the central enigma. There are three leading theories, each painting a different picture of our galaxy's history and future. The first idea is that these clouds are intergalactic rain, vast reservoirs of primordial gas left over from the formation of the universe itself, may still linger in the sparse space between galaxies. Occasionally, a clump of this ancient material falls into the Milky Way's gravitational grasp, plummeting down to fuel future generations of stars. The second theory is more violent. Our galaxy is a cosmic cannibal, having consumed smaller dwarf galaxies throughout its long life. High-velocity clouds could be the shredded remains of these galactic victims, their gas torn into long streamers by tidal forces, now swirling in chaotic orbits as a ghostly memorial to a long-ago feast. The third possibility is that they are material from our own galaxy, violently expelled from the disk by the combined fury of supernova explosions, only to now be falling back in a great cosmic recycling loop. Their role is crucial regardless of their origin. They are a primary source of new fuel. Stars are constantly burning through hydrogen, locking it up in their cores or blowing it back out into space in altered forms. For the galaxy to keep making new stars, it needs a fresh supply of pristine hydrogen. High-velocity clouds appear to be that supply, a delivery system for the raw material of creation. Maps of the sky in neutral hydrogen reveal them not as isolated curiosities, but as a complex, frothing sea of infalling streams and arcs, a hidden weather system of galactic proportions. They are the galaxy breathing in, a slow, mysterious inhalation that will, in time, become the breath of new suns. The raw fuel delivered by those high-velocity clouds is not the only thing raining down on our galaxy. The interstellar medium is also flooded with a relentless, invisible downpour of atomic shrapnel. These are cosmic rays, subatomic particles, mostly protons hurtling through space at nearly the speed of light. They carry more energy than anything we can create in our most powerful particle colliders on Earth. Their origin is one of the great detective stories of astrophysics, because by the time these particles reach us, all their clues are scrambled. A cosmic ray is not a beam of light you can trace back to a star. It is a charged particle, a tiny magnetized bullet. As it screams across the galaxy, the Milky Way's immense magnetic field acts like a cosmic maze, bending and twisting its path millions of times. By the time it finally slams into Earth's atmosphere, creating a shower of secondary particles we can detect, it is utterly lost. We have no idea which direction it originally came from. So how do we solve a mystery where all the witnesses have amnesia? We look for the cosmic accelerators themselves. The leading suspect for a century has been the shockwaves from supernova explosions. Picture the expanding shell of a supernova remnant like the Crab Nebula, plowing into the surrounding interstellar medium at thousands of miles per second. This creates a chaotic, moving frontier, a natural particle accelerator. Protons and electrons can get caught in this magnetic turbulence, bouncing back and forth across the shockwave, gaining a little more speed with each crossing until they are ejected at nearly light speed. It is a compelling and elegant idea, but the evidence is not conclusive. We see the glowing remnants, we detect the particles, but directly linking a specific cosmic ray to a specific supernova has been maddeningly difficult. This gap has opened the door to more exotic possibilities. Could stellar winds from massive, violent stars whip particles up to these energies? What about the furious environments around microquasars, stellar black holes that devour a companion star and spit out jets of plasma? Or even the unimaginable power of active galactic nuclei, where supermassive black holes in other galaxies launch jets that could pepper the entire universe with ultra-high-energy rays? The truth is, the interstellar medium is likely filled with the mixed signatures of all these engines. It is a cosmic soup stirred by countless explosions and eruptions. Each high-energy particle we detect is a message, but it is written in a language of pure force, and we are still learning how to read the return address. The mystery is not just where they come from, but how nature builds accelerators so much more powerful than anything we can conceive. Those cosmic rays do not travel through empty space, but through a universe threaded with invisible lines of force. This is the seventh mystery, the physics of magnetic fields in the interstellar medium. These fields are astonishingly weak, millions of times fainter than a common refrigerator magnet, yet they are everywhere. They weave through every nebula, every dust cloud, every vast expanse of near-nothingness. And despite their faintness, they hold a tyrannical influence over the structure of our galaxy. They guide the collapse of star-forming clouds, acting as a cosmic support beam that can slow or even prevent a cloud from collapsing under its own weight. They channel the paths of those high-energy cosmic rays, bending their trajectories into the scrambled mess that hides their origins. They even align the tiniest grains of interstellar dust, which in turn paints a hidden map across the sky. The central puzzle is how something so delicate can be so powerful, and where these pervasive fields even come from. One leading theory is that they are primordial, a fossil imprint from the universe's infancy, stretched and woven by the expansion of space itself. Another suggests they are generated and amplified by the churning motions of ionized gas within the galaxy, a kind of cosmic dynamo. The truth likely involves both, a seed field from the beginning of time that has been twisted and reinforced by eons of stellar winds and supernova shocks. We cannot see these fields directly, so how do we map the invisible? We use a property of light called polarization. Imagine starlight as a wave vibrating in all directions. When that light passes through a cloud of dust grains that have been aligned by a magnetic field, The grains act like tiny picket fences, only letting through light that vibrates in one specific direction. By measuring this subtle preference in the starlight from thousands of stars, astronomers can trace the orientation of the magnetic field lines across vast distances. The results are breathtaking. Visualizations of these measurements show the field lines not as neat, orderly patterns, but as a chaotic tapestry. They drape over the pillars of creation in the Eagle Nebula like ethereal threads, and they swirl in furious vortices around the expanding shells of supernova remnants. They are the galaxy's skeleton and its nervous system combined, a silent, pervasive force that sculpts the visible universe. Yet for all we can map, the fundamental question remains. Are we seeing the ancient handwriting of creation, or just the temporary scars from the latest galactic storm? The magnetic field is the universe's silent conductor, and we are only beginning to hear the first notes of its symphony. Those magnetic fields align particles of a substance so common it darkens the Milky Way, yet each speck is a world unto itself. Interstellar dust, a fine haze of microscopic grains, is far more than cosmic dirt. These tiny particles, most smaller than a wavelength of light, hold the eighth mystery of the medium, a complete and violent life cycle we are only beginning to trace. Their story begins in the furnaces of dying stars, in the swollen, cool atmospheres of aging red giants. Atoms like silicon, oxygen, and carbon link together in the relative calm, condensing directly from gas into solid modes. In the unimaginable violence of a supernova, the shockwave itself can forge new dust from the ejected stellar material in a single, catastrophic instant. Observations of supernova remnants like Cassiopeia show this process in action, with infrared telescopes detecting the warm glow of freshly synthesized dust just years after the explosion. But this is only the birth. To fulfill their cosmic role, these infant grains must grow. They drift into the cold, dark molecular clouds where they become the most important solid surfaces in the universe. Atoms and simple molecules from the gas freeze onto them, forming icy mantles. Here, in the frozen quiet, two carbon atoms can meet on a dust grain surface and stick, beginning a slow accretion that can build complex organic molecules layer by layer over millions of years. The dust grain is both a nursery and a shield. Its bulk protects the fragile ice mantles and the chemistry happening on its surface from the harsh ultraviolet radiation that would otherwise break everything apart. Without this dark, dusty blanket, the complex molecules that are the precursors to life could never form. Yet, for all their constructive power, dust grains are fragile and their lives are short on cosmic timescales. They are destroyed almost as quickly as they are made. The very shock waves from supernova that create new dust also blast through clouds, vaporizing older grains in a wave of heat and pressure. The fierce ultraviolet radiation from hot, young stars can also strip them apart, molecule by molecule. Stunning infrared images from telescopes like the Spitzer Space Telescope and the James Webb Space Telescope reveal this endless cycle in breathtaking detail. What appears as a dark, starless rift in a visible light image, like the Inkai lanes in the Milky Way or the famous Horsehead Nebula, glows with an ethereal, sculpted light in the infrared. That glow is the thermal radiation from the dust itself, warmed by nearby stars. We see vast, hidden landscapes where pillars of dust are simultaneously being eroded by stellar radiation and sheltering new stars being born within them. Each tiny grain is a temporary vessel, a cosmic way station where matter transitions from the diffuse gas of dead stars to the complex chemistry of new worlds. Their existence is a constant, delicate balance between creation and destruction, a cycle written in shadows and infrared light that governs the very texture of the galaxy. That delicate dance of dust creation and destruction sets the stage for the universe's greatest act of construction, but the curtain does not rise on its own. The ninth mystery asks a deceptively simple question. What flips the switch? We know stars are born in those cold, dark molecular clouds, vast reservoirs of hydrogen and dust. Gravity wants to pull them inward to collapse them into brilliant new suns. Yet for millions of years, these clouds simply drift, stable and dormant. Something must push them over the edge, and the identity of that cosmic trigger is hotly debated. One of the leading suspects is a force of pure destruction, a supernova shockwave. Picture the expanding million-mile-per-hour wall of debris from a dying star slamming into a quiet molecular cloud. The impact is not just a push, it is a profound compression. It squeezes vast regions of the cloud, creating dense knots and filaments within the gas. In these compressed pockets, gravity's whisper suddenly becomes a shout, overwhelming the cloud's internal pressure and magnetic support. We see compelling evidence for this in places like the Taurus molecular cloud, where the faint, expanding shells of ancient supernova remnants appear to be physically interacting with active star-forming regions. It is a story of stellar death directly seeding stellar birth, but a supernova is not the only candidate. Sometimes the trigger may be a quieter, more gradual collision. Giant molecular clouds themselves can drift into one another in the slow-motion traffic of the galactic disk. When two such clouds merge, their gas does not simply pass through, it piles up at the collision front. This pile-up creates the same critical density needed for gravity to take over. Computer simulations of these cloud collisions show beautiful, intricate webs of gas forming at the interface, with dense cores condensing out like beads on a cosmic string, each a potential stellar nursery. Then there is the grand architectural theory, spiral density waves. Our Milky Way is a spiral galaxy, and those majestic arms are not static structures but moving patterns of compression, like traffic jams in the flow of stars and gas. As a molecular cloud enters a spiral arm, it gets caught in this slow-moving wave of higher density. The cloud is squeezed not by a single explosion, but by the entire gravitational architecture of the galaxy itself. This could explain why we see the brightest, most prolific star-forming regions, like the Orion Nebula, lined up along spiral arms. They are lit up by the galactic traffic jam. So why do some clouds burst with new stars while others slumber for eons? The answer likely lies in a cloud's history and environment. A lone, isolated cloud may never encounter a trigger. It could slowly evaporate under ambient starlight, never giving birth. But a cloud drifting through a spiral arm, or one sitting near a community of massive stars destined to go supernova, lives in a cosmic danger zone, a zone where destruction is the prelude to creation. Visualizing this through time-lapse simulations reveals the epic scale. Watch a serene cloud of gas, light years across, drift for millions of years. Then a faint ripple approaches from one side, the shockwave from a distant cataclysm. As it passes through, the entire cloud stirs, convulses, and begins to fracture into glowing filaments. Pinpricks of light ignite within those filaments, the first protostars, their radiation soon blowing away the very cloud that birthed them. The trigger is the first domino in a chain reaction that lights up the darkness, and we are still identifying all the hands that can give it a push. The violent birth of new stars may forge the future, but the ancient light from the oldest stars reveals a missing piece of the past. This is the cosmological lithium problem, a discrepancy between our grandest theory of creation and the hard evidence written in starlight. According to the detailed calculations of Big Bang nucleosynthesis, the first few minutes of the universe produced specific, predictable amounts of the lightest elements. Hydrogen and helium came out in vast quantities, perfectly matching what we see. But for lithium, the third lightest element, the numbers are stubbornly wrong. The oldest stars in our galaxy, which formed from nearly pristine gas over 13 billion years ago, contain only about 1/3 of the lithium-7 that the Big Bang models say should be there. It is as if the universe's recipe book has a misprint. Where did all that primordial lithium go? the interstellar medium might hold the key to this billion-year-old mystery. One compelling theory suggests that lithium did not simply vanish. Instead, it was systematically destroyed in the interstellar gas long before those ancient stars ever formed. Lithium is a fragile atom. At the temperatures found inside stars, it is easily broken apart, but the crucial destruction might have happened not in stars, but in the diffuse gas between them. Imagine the early galaxy filled with hot, turbulent gas from the first supernova. In this chaotic environment, lithium atoms could have been transported to regions of intense heat or exposed to powerful fluxes of cosmic rays. A single collision with a high-energy particle could shatter the delicate lithium nucleus. Over hundreds of millions of years, this slow, pervasive destruction in the interstellar medium could have depleted the galactic reservoir before the oldest stars had a chance to incorporate it. To visualize the problem, picture a simple bar graph. One bar, labeled Big Bang Prediction, stands tall, representing the theoretical abundance of lithium-7. Right beside it, a second bar, labeled Observed in Old Stars, reaches only 1/3 of that height. The gap between them is the mystery, a stark, empty space demanding an explanation. This gap is not just a minor accounting error. It challenges our understanding of the universe's first moments and the chemical evolution of everything that followed. If the interstellar medium was the site of this destruction, it means the medium is not a passive backdrop. It is an active chemical processor capable of altering the fundamental ingredients of the cosmos before they ever reach a star. Solving the lithium problem would require us to rewrite a chapter of galactic history, one where the quiet spaces between the stars played a decisive role in erasing a key piece of evidence from the dawn of time. Our own solar system floats within a cosmic cavity of its own, a vast and nearly empty chamber in the interstellar fog. This is the local bubble, a region of exceptionally hot, thin gas roughly 1,000 light-years across, and we are drifting almost exactly at its center. The space around us is not uniformly filled. Instead, we are inside a giant, irregular cavern. Its walls a glowing tapestry of cooler, denser gas and dust. The existence of this bubble solves a long-standing puzzle. For decades, astronomers wondered why, in almost every direction we look for about 500 light-years, we see so little of the thick dust that otherwise obscures our view of the distant galaxy. The answer is that we are sitting in a cleared-out zone. But what kind of force could have carved out such an immense volume? The evidence points to a history of unimaginable violence, a chain reaction of stellar death that occurred right in our galactic neighborhood. Between 10 and 20 million years ago, a cluster of massive stars born close together lived fast and died young. One by one, they exploded as supernova. Each titanic detonation sent a blistering shockwave of million-degree gas plowing into the surrounding interstellar medium. Like a cosmic snowplow, these successive waves pushed the cooler gas and dust outward, piling it up into the intricate glowing walls we see today. The bubble is not a perfect sphere. It is a frothy, complex structure because we are not alone in this process. Our local bubble is just one of many in the galaxy, like holes in a cosmic sponge. Its boundaries are where it presses against other, neighboring bubbles blown by different star clusters. In some directions, the walls are thick and bright, like the famous Orion molecular cloud complex, a star-forming region that is literally on our doorstep. In other directions, the walls are tenuous, and we can peer right through into the next bubble over. Modern 3D maps, built from painstaking distance measurements to thousands of stars by missions like the European Space Agency's Gaia satellite, reveal this structure in stunning detail. We can now visualize our sun's position not as a point in a flat map, but as a tiny dot inside a grand, sculpted cavity, its surface is defined by the ghosts of ancient explosions. This local architecture has a direct effect on our planet. The hot, thin gas inside the bubble is a poor shield. It means that cosmic rays, those high-energy particles from across the galaxy, have a relatively clear shot at our solar system once they penetrate the bubble's walls. The density and magnetic fields of the bubble's interior help modulate the flux of these particles that rain down on Earth, potentially influencing cloud formation and even the mutation rate of life over deep time. We are living inside a fossil, a monument to a series of cataclysms that shaped our celestial environment long before humans walked the Earth, and its delicate structure continues to guide the river of energy flowing from the galaxy into our own backyard. Deep within the sculpted cavern of the local bubble, another kind of signal whispers from the dust itself, a signal that for years was mistaken for simple noise. Across the entire sky, a faint, mysterious glow permeates the microwave part of the spectrum. This is the anomalous microwave emission, or AIM, and its discovery rewrote our understanding of how the smallest particles in the universe can shine. When astronomers first mapped the cosmos in microwave light, they expected to see the smooth, ancient glow of the cosmic microwave background, the afterglow of the Big Bang. They also expected to see contributions from synchrotron radiation, given off by electrons spiraling in magnetic fields, and thermal emission from warm dust. But there was an extra component, a diffuse shimmer that didn't match any of these known processes. It was too broad and too bright to be explained by the standard models. For a time, it was dismissed as an artifact, an unexplained fuzz in the data. The breakthrough came when researchers realized this glow was tightly correlated with the presence of interstellar dust, but not with its heat. This was not a thermal glow. The culprit, it seems, is the tiniest dust grains of all, nanoparticles only a few billionths of a meter across. These minuscule specks, likely made of carbon or other hardy materials, are sent into a furious spin by collisions with individual atoms or by the pressure of starlight itself. As they spin at mind-boggling rates, billions of rotations per second, they develop a tiny electric dipole, a slight imbalance of charge. A spinning dipole is a microscopic radio transmitter. This phenomenon, called electric dipole emission, causes these nanograins to broadcast a faint but detectable signal in the microwave band. Think of it as the universe's most diffuse radio station, its signal generated not by intent, but by the chaotic ballet of light and atoms against the smallest possible surfaces. All sky maps from missions like the Planck satellite tell the story visually. When you subtract the known contributions from the cosmic microwave background, synchrotron radiation, and thermal dust, a new, intricate pattern emerges. The AIM signal paints a faint, filamentary web across the galaxy, tracing regions of particular dust density and activity. It is strongest in specific, dusty clouds like the Rho Ophiuchi complex, a nearby stellar nursery. Yet for all this progress, the exact physical process remains debated. Are the grains primarily spinning from random atomic collisions, or is the kick from ultraviolet photons striking them a process called photoelectric emission, the main driver? The precise composition of the grains is also a mystery. Certain carbon-based structures or molecules like polycyclic aromatic hydrocarbons are leading candidates, but the definitive fingerprint is elusive. This isn't just a curiosity. AIM is a contaminant. To see the pristine infant universe in the cosmic microwave background, we must subtract every source of foreground emission from our own galaxy. AIM is one of the most subtle and tricky of these foregrounds. If we mischaracterize it, we risk introducing false patterns into our maps of the early cosmos, potentially distorting our understanding of fundamental physics. So, studying this anomalous glow is an act of cosmic cleaning. It is the process of listening to the hum of spinning dust so we can silence it, allowing the true echo of the Big Bang to ring through with perfect clarity. The universe's faintest radio transmission, it turns out, is static we must decode to hear an even older song. The faint hum of spinning dust exists within a far more chaotic symphony, a realm of pure, violent motion. The interstellar medium is not a placid sea of gas. It is a churning, supersonic fluid, a cosmic maelstrom where motions exceed the speed of sound by 10, 20, even 50 times over. This is the role of turbulence, and its origin is a fundamental mystery shaping the galaxy's structure. What force stirs this vast cauldron? The prime suspects are the usual agents of cosmic violence. Supernova explosions send continent-shattering shockwaves rippling through the medium for thousands of light years. The fierce stellar winds from massive, young stars act like million-mile-per-hour sandblasters, carving out cavities and injecting furious energy. Even the slow, grand rotation of the galaxy itself shears and stretches the gas, introducing a baseline level of disorder. Yet for all these powerful drivers, there is an equal mystery of dissipation. Turbulence left to its own devices should bleed its energy away quickly, decaying into a calm whisper in a surprisingly short time, cosmically speaking. The fact that we see it everywhere means it is being constantly reignited, a perpetual storm requiring a constant input of energy from stellar births and deaths. This relentless churning plays a surprisingly delicate role. It acts as a cosmic regulator, a brake on gravity's ambitions. Without turbulence, a molecular cloud would collapse under its own weight in a single, catastrophic free fall, forming a frenzy of stars all at once. Instead, the chaotic, supersonic motions create a network of internal pressure, propping the cloud up like an invisible scaffold. It fragments the cloud into a complex, hierarchical tapestry, a fractal structure where every filament, when zoomed in, reveals smaller filaments and knots. This is why star formation is inefficient and slow. Gravity must work against this turbulent support, slowly draining energy from the eddies and vortices to coalesce a dense core. Visualizing this requires supercomputer simulations. Watch as a cube of simulated gas, light years across, begins in relative calm. Then inject energy mimicking supernova shocks. Instantly, the scene erupts. Swirls and tendrils of gas form, collide, and shear apart in a breathtaking dance of supersonic flows. Shock fronts ripple through the medium, compressing some regions into glowing sheets while rarefying others into vast voids. The structure is not random. It is a self-similar cascade of energy from the largest scales down to the smallest, a signature of true turbulence. Set to epic, driving music, this simulation is not just a visualization of chaos. It is the blueprint for creation. The very knots and filaments forged in this violent forge are the prenatal cradles of stars. The turbulence determines their masses, their spacing, and ultimately the destiny of the solar systems they will one day host. The galaxy breathes in this storm, and within its most violent pockets, it gives birth to new light. That same turbulence is part of a grander, galactic-scale circulation system, a cosmic weather pattern that may recycle the very substance of stars. The galactic fountain model proposes a breathtaking vision of our galaxy not as a static disk, but as a living, breathing entity with its own hydrological cycle. Here, the role of water is played by million-degree gas, and the pump is the titanic force of supernova. According to this theory, when a massive star explodes in the disk of the Milky Way, it does more than just carve out a local bubble. The combined energy from many such explosions in a star-forming region can launch a colossal plume of superheated gas. This material, enriched with the heavy elements forged in stellar cores and during the supernova itself, blasts upward, punching through the thinner layers of the galactic disk and soaring high into the galactic halo, the sparse, spherical region that surrounds the visible pinwheel of stars. For a time, this hot gas hangs in the halo, a vast, invisible cloud tens of thousands of light years above the starry plane. But space is cold and the halo offers little insulation. Slowly, over millions of years, this ejected gas begins to radiate away its tremendous heat. As it cools, it condenses into denser clumps and filaments. Now much cooler and heavier, these clumps succumb to the galaxy's relentless gravity. They begin a long, slow fall back toward the disk, accelerating as they go. By the time they come screaming down, they are the high-velocity clouds we detect, the mysterious rain of hydrogen and heavy elements falling from the galactic sky. The evidence for this model is compelling but circumstantial. X-ray telescopes like Chandra have detected the faint glow of million-degree gas in the galactic halo, the presumed steam rising from the fountain. Observations also show that many high-velocity clouds are indeed enriched with heavy elements like oxygen and silicon, proving they are not pristine primordial gas, but recycled material that has been inside a star. Furthermore, their distribution and motions are consistent with an origin in the disk and a subsequent fall back down. Yet, the model faces significant challenges. Not all high-velocity clouds show the same level of heavy elements. Some appear too pristine to have come from the violent death of stars. This suggests multiple origins are at play. Some clouds may be intergalactic in fall, while others are true fountain rain. The cooling process in the halo is also poorly understood. Can the hot gas cool efficiently enough to form the dense, cold clouds we see, or does it need additional help from mixing with cooler halo material? Visualizing this cycle transforms our understanding of the galaxy. Sophisticated computer simulations show it beautifully. Watch a side view of a simulated spiral galaxy. From the bright, thin disk, brilliant points of light flare supernova. From these points, great plumes of translucent, red-hot gas surge upward, arcing gracefully into the dark halo. As they rise, they change color, shifting from red to blue as they cool. At the apex of their arc, they fragment into shimmering blue-white droplets. These droplets then streak back down toward the glowing disk like celestial comets, impacting the spiral arms and seeding them with fresh, enriched material. If this fountain is the primary mechanism, it means the heavy elements essential for planets and life. The carbon in our bones, the iron in our blood, are not just made in stars, but are distributed through a majestic billion-year cycle of explosive eruption, lofty cooling, and gentle, life-giving rain. The galaxy is not just an island of stars, it is a geyser perpetually erupting, its fallout nurturing the next generation of worlds. That majestic galactic fountain cycles matter we can see, but our cosmic accounting reveals a staggering shortfall. Across the entire observable universe, we can only locate about half of the normal matter, the protons and neutrons or baryons, that our best models of the Big Bang insist must exist. This is the missing baryon problem, and it is not about dark matter. It is about the ordinary stuff of stars, planets, and us seemingly vanishing into thin space. The inventory is stark. If we take a theoretical pie chart of the universe's total matter and energy, only about 5% is this normal baryonic matter. The rest is the mysterious dark matter and dark energy. Yet, when astronomers add up everything they can actually detect, all the stars, all the glowing gas in galaxies and clusters, all the dust, they only account for roughly half of that already small 5% slice. Where is the rest of the atoms? The leading suspect is not in the bright galaxies, but in the vast, lonely spaces between them. Theorists predict that a cosmic web of diffuse, superheated gas stretches across the universe, a filamentary structure tracing the dark matter scaffolding. This is the warm, hot intergalactic medium, or WIM. It is not cold, dense, and easy to see like a nebula. It is a sparse, million-degree plasma so thin that a single coffee mug full of it would contain only a handful of atoms, yet it fills volumes so immense it could comprise the missing half of all normal matter. Detecting it is a monumental challenge. A gas that hot glows faintly in X-rays, but it is so diffuse that its signal is drowned out by brighter sources. Our best hope is to use it as a cosmic filter. When the brilliant light of a distant quasar travels billions of light years to reach us, it passes through these faint filaments. The WIM million-degree temperature means the oxygen and other heavy atoms within it are stripped of most of their electrons, becoming highly ionized. As the quasar's light passes through, these ions absorb very specific, subtle wavelengths of X-ray and ultraviolet light. It is like finding the silhouette of a nearly invisible ghost by the few stars it blots out in a distant city's skyline. These absorption lines are the telltale fingerprints, and after decades of searching, instruments like the European Space Agency's XMM Newton telescope have begun to find them, tentatively confirming that the WIM is real and holds a substantial amount of mass. This missing matter forms a direct bridge to the interstellar medium. The WIM is the ultimate source and destination. It is the primordial reservoir from which galaxies first condensed, and it is also the final resting place for material violently ejected from galaxies by supernova fountains and galactic winds. The circumgalactic medium, the space immediately surrounding a galaxy like our own, is likely where the hot interstellar medium from our galactic fountain meets and mixes with this even hotter intergalactic plasma. Visualize a new pie chart. The full baryonic slice is now divided. A small sliver is locked in stars. A slightly larger portion is in the cool and warm interstellar gas and dust we've been exploring. But the largest piece of the normal matter pie, nearly half of it, is colored as a faint, wispy haze labeled WIM. This changes our entire picture. The interstellar medium is not an isolated ecosystem. It is a dynamic interface, constantly exchanging matter and energy with a far vaster, hotter, and invisible ocean that binds the galaxies together. The atoms in your body were once part of that ocean, and they may one day return to it. The search for the missing baryons is a hunt for the universe's hidden skeleton, the hot, thin blood of the cosmic web that holds the visible universe aloft. The frozen mantles cloaking interstellar dust grains are more than just decoration. They are microscopic chemical factories operating in the deepest cold of space. Within the shielded heart of a dark molecular cloud, temperatures plunge to just 10 degrees above absolute zero. Here, individual atoms and simple molecules drifting through the void do not bounce off a dust grain, they stick. A layer of frost begins to build, a mix of water ice, carbon monoxide, carbon dioxide, methane, and ammonia. On this tiny, frozen stage, chemistry that would be impossible in the gas phase unfolds with profound implications. The surface of the ice acts as a meeting place and a catalyst. Two hydrogen atoms, for instance, might wander alone in the gas for 1 million years without ever finding each other to form molecular hydrogen. But on a dust grain, they both get trapped. They slide across the icy surface in a quantum mechanical crawl called tunneling, eventually finding one another and linking up. This process scales up to incredible complexity. A carbon monoxide molecule frozen in the ice can be bombarded by hydrogen atoms, slowly hydrogenating step by step into formaldehyde, then methanol, and potentially even more complex organic molecules. These ices are the universe's frozen starter kit for probiotic chemistry. The mystery intensifies when a new star ignites at the cloud's heart. The previously dark, cold nursery is flooded with heat and ultraviolet radiation. This should be a destructive force, breaking apart the delicate molecules forged over eons. Yet, observations reveal something astonishing. Instead of simply erasing the chemistry, the stellar radiation cooks the ices, driving a new wave of complex reactions. It is a process called photochemistry. The ultraviolet photons provide the energy to break molecular bonds and rearrange the fragments into even larger, more complex species. Simple ices are transformed into a rich organic residue, a tar-like substance that could coat the first pebbles and planetesimals in a young solar system. We know this because our telescopes can taste the ices from light years away. Instruments like the infrared spectrometers on the James Webb Space Telescope do not see images, they see fingerprints. When starlight from a background star or a newly forming protostar passes through or reflects off a cloud, the ices within absorb specific colors of infrared light. The resulting spectrum is a barcode, each dip and line revealing a molecule's presence. The graphs are stunning. A smooth curve is interrupted by deep, sharp valleys. One valley at a wavelength that screams water ice, another for carbon dioxide, another for methane, and a forest of smaller lines indicating more complex organics. By comparing these cosmic spectra to ices created and zapped with radiation in laboratories on Earth, we are decoding the recipe. The great unanswered question is how far this chemistry can go before the heat of a nascent star system boils it all away. Do these irradiated ices become the direct feedstock for comets, which then deliver water and organics to young planets like early Earth? The icy mantles on dust are the universe's first cookbooks, and we are just beginning to read their frozen, transformative pages. These frozen mantles of ice and organics cling to the densest, coldest objects in the galaxy, the true cradles of creation. Deep within the sprawling architecture of a molecular cloud, gravity carves out its final sanctuaries, dense, dark cores of gas and dust so cold and isolated they are named prestellar cores. These are the embryos of stars, the exact point where the diffuse interstellar medium transitions into a luminous sun. Yet their internal physics remains one of the most elusive mysteries, for they are opaque to almost all light, shrouded in their own dark material. To see them, we must listen to the faintest radio whispers of the molecules shivering within. A perfect example is Barnard 68, a dark smudge in the constellation Ophiuchus. In visible light, it is a hole in the star field, an ink blot against the Milky Way. But through the eyes of a radio telescope like the Atacama Large Millimeter Array, it transforms. The core reveals itself as a near-perfect sphere of cold ammonia and dust, its edges sharp against the surrounding void. It is a snowball in the making, poised on the knife's edge of collapse. The central question is what happens next, deep within that shadow. Why does one core like this condense down to a single, solitary star like our Sun, while another fragments into a chaotic litter of stellar siblings? The answer lies in a hidden battle between two invisible forces, the cloud's innate turbulence and its magnetic field. Think of the core as a spinning ball of yarn. As gravity pulls it inward, any initial spin is magnified, just as an ice skater spins faster by pulling in their arms. If this spin is too strong, the core cannot collapse into a single point. Instead, it flattens into a disk, and that disk can become unstable, breaking apart into 2, 3, or even more distinct knots, each destined to become a star. This is how most stars are born, in pairs or small families. Our Sun, a solitary star, is somewhat of an outlier. Its birth core must have been exceptionally quiet and slowly rotating, allowing gravity to proceed without this fragmenting spin. But rotation is only part of the story. The core is also threaded with magnetic field lines. These lines act like cosmic rubber bands, providing support against collapse. For a core to form a star, it must find a way to shed both its spin and its magnetic field, a process called magnetic braking. The current theory suggests that the field lines help transfer the core's spin out into the surrounding cloud, slowing its rotation. Yet, observations are frustratingly sparse. The magnetic fields inside these cold, dark cores are fiendishly difficult to measure, and the fragmentation happens on scales smaller than most telescopes can resolve. We are left with computer simulations that show beautiful, branching possibilities. In one simulation, a turbulent core collapses into a tangled web of filaments, with multiple bright points of light protostars igniting along them. In another, a magnetically dominated core collapses more gracefully into a single, dominant object with a faint, whirling disk. The reality is likely a spectrum, and where a core falls on that spectrum determines the destiny of an entire planetary system. The solitude of our Sun, the binary dance of Alpha Centauri, the crowded nursery of the trapezium stars in Orion, all were decided in the silent, frozen physics of these dark cores. We are only now developing the tools to peer into these wombs of stars, to understand the first moments when chaos decides between a lone star and a stellar dynasty. That silent, frozen physics of star birth is governed by the simplest atom in the cosmos, whose faintest whisper built the map of our galaxy. This is the 21-centimeter line, the signature of neutral hydrogen, and it is both a cornerstone of radio astronomy and the source of a profound new mystery. The signal itself comes from a humble quantum dance inside every lonely hydrogen atom drifting in space. A hydrogen atom is just one proton and one electron. Both of these particles possess a property called spin. Like tiny, intrinsic magnets, they can spin in the same direction or in opposite directions. The opposite configuration holds a tiny bit more energy. Once in a great while, about once every 10 million years for a given atom, an electron will spontaneously flip its spin to a line opposite its proton. That minuscule release of energy escapes as a radio photon with a wavelength of precisely 21 centimeters. It is an incredibly rare event per atom, but space contains a staggering number of atoms. That collective whisper, when gathered by massive radio dishes, paints our most complete picture of the Milky Way's structure. By measuring the slight Doppler shifts in this line, astronomers chart the rotation of our galaxy, revealing its spiral arms in hydrogen's glow where optical telescopes see only darkness. For decades, this signal was a trusted tool, a steady beacon in the radio sky. Then we tried to listen for its echo from the dawn of time, and the universe played a trick on us. When we look back to the cosmic dark ages, just a few 100 million years after the Big Bang, we expect to see the 21-centimeter line in absorption. The first stars and galaxies were switching on, their intense ultraviolet radiation exciting the vast sea of primordial hydrogen around them. This should cause the gas to absorb the even more ancient background radiation from the Big Bang itself at that specific 21-centimeter frequency. In 2018, an experiment called EDGES, a small, table-sized radio antenna in the remote Australian outback, reported a detection of this ancient absorption signal. But the signal was far too strong. The dip in the radio spectrum was about twice as deep as the most extreme theoretical models allowed. It was as if the primordial hydrogen was far colder than anyone predicted, or the background radiation from the early universe was far hotter. Either scenario requires exotic new physics. One startling possibility is that this cold hydrogen was interacting with something even colder, perhaps the elusive particles of dark matter. If dark matter particles have even a tiny interaction with normal matter, they could have siphoned heat away from the hydrogen gas, cooling it dramatically below the expected temperature. Another possibility is that our understanding of the radiation environment in the early universe is completely wrong. The data from EDGES remains controversial, and newer experiments are seeking to confirm it. The pursuit now is to build ever more sensitive radio telescopes on the far side of the moon, where the Earth's radio chatter cannot interfere, to listen for this faint, ancient sigh. Visualizing the signal is to see a simple graph. A smooth curve representing the cosmic microwave background is suddenly gouged by a deep, narrow valley at a frequency corresponding to when the universe was only 180 million years old. The depth of that valley is the anomaly, a deviation from the predicted dotted line that has sent cosmologists back to their chalkboards. This humble spin flip, the most fundamental tick of the cosmic clock, may have recorded a conversation between the first starlight and a hidden component of reality, a conversation we are only now beginning to overhear. Those ancient echoes of hydrogen connect us to the dawn of time, but a far more recent eruption from our galaxy's heart has left a pair of scars we can see today. Reaching high above and below the Milky Way's disk, the Fermi bubbles are colossal structures of ultra-high-energy gamma-ray light. They are not the radio lobes mentioned earlier, but they are intimately related, nested within them like a ghost within a ghost. Their discovery by the Fermi Gamma Ray Space Telescope revealed a violent event that punched through the thin galactic atmosphere, and their ongoing interaction with the interstellar medium is a live demonstration of cosmic violence. The leading theory is that our supermassive black hole, Sagittarius A star, had a dramatic feeding episode sometime in the last few million years. As it consumed a large cloud of gas, it launched two opposing jets or a spherical outflow of relativistic particles, matter moving at a significant fraction of light speed. This jet or wind plowed into the existing halo of hot gas surrounding the galaxy. The result was not a gentle push, but a supersonic shockwave. Visualize a speedboat suddenly accelerating across a still lake. The prow of the boat pushes water aside, creating a smooth, raised bow wave ahead of it and a turbulent, foaming wake behind. The Fermi bubbles are that bow wave, a pair of gigantic, continuous shocks that are still propagating outward. At their edges, the million-degree particles from the black hole's outburst slam into the cooler, denser gas of the galactic halo. This collision compresses and heats the halo gas, creating a bright rim that glows in X-rays, which we detect with telescopes like the Chandra X-ray Observatory. Inside the bubbles, the medium is radically different. It is filled with that fast-moving, thin plasma from the black hole, a chaotic soup of magnetic fields and energetic particles. This is where the gamma rays are born. As electrons are accelerated to near light speed within this maelstrom, they interact with the low-energy light that fills all of space, the cosmic microwave background. In a process called inverse Compton scattering, these ultra-fast electrons slam into the faint background photons, boosting them to the immense energies of gamma rays. This tells us the bubbles are not empty cavities, they are active accelerators still churning with power. The debate over their age hinges on this interaction. If the outburst was a single, short blast, the bubbles would be like an expanding shell, and we could estimate their age from their size and speed. But the gamma-ray emission is remarkably uniform and bright all the way from the galactic center to their edges, about 25,000 light-years up. This suggests the shock might still be actively being driven, perhaps by a sustained wind from the black hole that lasted for tens of thousands of years. Composite images that layer gamma-ray, X-ray, and radio data are essential to understanding this story. In these multi-wavelength portraits, the narrative unfolds. The gamma-ray data from Fermi paints the vast, faint, ghostly outlines of the bubbles themselves, two enormous ovals stretching north and south of the galaxy. Superimposed on this, the X-ray data from Chandra reveals intricate filamentary structures at the bubble's rims, the shocked and compressed gas of the halo. Meanwhile, radio maps show the fainter, larger radio lobes that encompass the entire structure, possibly an older relic of a related event. Seeing these datasets combined transforms abstract data into a cosmic crime scene. It shows the shock front's location, the turbulent material behind it, and the larger context of the galactic center's violent history. The Fermi bubbles are a testament that the interstellar and circumgalactic medium is not a passive backdrop. It is a recording medium, capturing and holding the imprint of the galaxy's most powerful outbursts. We are witnessing the aftermath of a roar from the galactic core, a roar whose echo is still shaping the thin gas far above our heads. A fundamental element of life is telling two different stories in the cosmos. When astronomers measure the amount of oxygen in glowing nebulae, the results depend entirely on how they look. One method uses faint, forbidden lines visible in optical light, while another relies on bright, ultraviolet lines. In theory, they should agree, revealing how much of this critical element has been forged by generations of stars and scattered into space. In practice, they disagree, often by a factor of 2 or more. This is not a small calibration error. It is a direct challenge to our understanding of how stars enrich the universe. Oxygen is a primary product of massive stars, created in their cores and blasted out by supernova. Tracking its abundance is how we measure the chemical evolution of a galaxy. its journey from primordial simplicity to the complexity needed for planets and life. If we cannot accurately measure this cornerstone element, our entire cosmic chemical census is built on shaky ground. The conflict points to a deep flaw in our models. The optical method studies so-called forbidden lines, which are incredibly faint and only occur in the ultra-low-density environment of a nebula. The ultraviolet method looks at stronger, more direct transitions. For them to disagree so dramatically suggests something is wrong with our atomic data, the fundamental physics of how oxygen atoms absorb and emit light, or more intriguingly, with our understanding of the nebulae themselves. Perhaps these clouds are not as uniform as we assume, containing tiny, dense knots of material that affect one type of measurement more than the other. Maybe temperature fluctuations within the nebula are far more severe than our smooth models account for. The visual evidence is stark. A simple comparative graph tells the story. On one axis, you have oxygen abundance measured from ultraviolet lines, showing a steady, rising trend. On the other axis, you have abundance from optical forbidden lines, tracing a parallel but consistently lower path. The two lines never meet, separated by a persistent gap that spans different types of nebulae across different galaxies. This gap is the mystery. Resolving it means either recalibrating the universe's chemical ledger or reimagining the turbulent inner life of these beautiful, glowing clouds. Until we do, we cannot say for certain how much of the breath we take was forged in the hearts of distant, dying suns. The delicate organic molecules and dust grains we find in space should not last a day in some of the galaxy's most violent neighborhoods. Near the blistering surfaces of massive stars, ultraviolet radiation floods space with a power that can shred chemical bonds in an instant. Within the expanding fury of a supernova remnant, shock waves blast through at thousands of miles per second, a tempest of heat and pressure that should vaporize everything in its path. Yet, against all logic, we find molecules and dust surviving, even thriving, in these hostile zones. Their resilience forces us to rethink the life cycle of interstellar material. One of the most revealing cosmic laboratories is a structure called the Orion Bar. This is not a place to get a drink. It is a photodissociation region, a razor-thin frontier where the fierce light from the young, hot stars of the Orion trapezium slams into the surrounding molecular cloud. The ultraviolet radiation here is so intense it ionizes and breaks apart molecules, creating a wall of glowing gas. According to simple theory, this wall should be a dead zone for chemistry. But when we point our most powerful infrared and radio telescopes at it, like the James Webb Space Telescope, we see something astonishing. The bar is shimmering with the signatures of complex organic molecules. How can this be? The secret is shielding an astonishingly fast reformation. Picture the edge of the molecular cloud as a rugged, fractal coastline, not a smooth wall. Dense knots and pillars of gas and dust cast long shadows, creating tiny pockets of safety where molecules can hide. Within these shadows, the destructive ultraviolet light is reduced to a faint glimmer, allowing chemistry to continue. Even more fascinating is what happens right at the ionization front itself. As molecules are broken apart, their fragments, carbon ions, hydrogen atoms, oxygen, are left in an incredibly dense, energetic soup. In this chaotic environment, three body collisions become possible, where three particles meet simultaneously and stick. This allows for the rapid reformation of simple molecules, which can then quickly build into more complex ones in a frantic cycle of destruction and rebirth. It is a cosmic game of whack-a-mole, where new molecules pop up as fast as the radiation can knock them down. The same principle applies to dust grains in supernova remnants. We once thought a supernova's shockwave would destroy all the dust in its vicinity, but observations tell a different story. In the remnant Cassiopeia A, we see not only ancient dust that survived the blast, but also vast quantities of new dust forming in the cooling ejecta. The expanding shell creates its own shielded environments. Dense clumps of material within the remnant can be self-shielding, protecting their interiors from the full fury of the shock. Meanwhile, as the hot gas behind the shockwave expands and cools, atoms condense directly onto surviving grain fragments, reforming them sometimes faster than the radiation can erode them. This reveals a universe far more stubborn and resourceful than we imagined. The interstellar medium is not a passive victim of stellar violence. It is an active participant using chaos as a catalyst. Dense structures provide sanctuaries, and the very energy that destroys becomes the engine for rapid reconstruction. The survival of these molecules means the ingredients for life are not confined to quiet, dark nurseries. They are forged and hardened in the galactic furnaces, making them robust enough to potentially seed planets even in systems born from fire. Our galaxy's internal storms and chemistry are just a single thread in a tapestry of staggering scale. The interstellar medium does not end at the Milky Way's halo. It connects, becoming part of something far vaster and more structured, the cosmic web. This is the large-scale distribution of all normal matter in the universe, a ghostly architecture of filaments, walls, and immense voids that stretches across billions of light years. Gravity, acting on both dark matter and the ordinary gas, has woven this web over the eons since the Big Bang. Dense knots where filaments intersect are the galaxy clusters, the great cities of the cosmos. The long threads connecting them are rivers of diffuse, hot gas, and the empty spaces between the voids are cosmic deserts, nearly devoid of galaxies and most normal matter. This grand pattern raises a profound question about the interstellar medium on the largest scales. How uniform is it? The answer is not uniform at all. The universe is frothy, a sponge of matter and emptiness. This uneven distribution is a direct record of the initial conditions of the cosmos, tiny quantum fluctuations in the infant universe magnified by gravity into the majestic structure we see today. We can map this web not by taking a direct picture. It is too faint and vast, but by using the light of the universe's most brilliant beacons as a cosmic flashlight. When astronomers point their telescopes at a distant quasar, the luminous core of an active galaxy billions of light years away, they do not see a clean spectrum. They see a forest. The quasar's light on its long journey to us passes through countless filaments and clouds of the intergalactic medium, the sparse gas that exists between galaxies. Atoms in these clouds, primarily hydrogen, absorb very specific wavelengths of the quasar's ultraviolet light. Each cloud at a different distance and therefore moving at a different speed due to the expansion of the universe, leaves a unique absorption line at a slightly shifted position in the spectrum. The result is a breathtaking sight. Where there should be a smooth, bright continuum from the quasar, the spectrum is instead carved into a dense thicket of dark absorption lines. This is the Lyman alpha forest, and each line is a single tree representing a cloud or filament of hydrogen intersected by the quasar's beam. By studying thousands of quasars, we can triangulate this forest in 3 dimensions. It allows us to build a statistical map of the cosmic web's gaseous component, revealing its filamentary structure and how it has evolved over time. The visualizations from large-scale surveys like the Sloan Digital Sky Survey are humbling. They show the universe not as a random scatter of galaxies, but as an intricate, interconnected neural network of light, with brilliant galaxy clusters at the nodes and faint, wispy tendrils of gas tracing the connections between them. Vast spherical voids, millions of light years across, punctuate the structure, regions where the cosmic web has drained away. This tells us the interstellar and intergalactic medium is the true substrate of the cosmos. Galaxies are merely the glittering condensations that form where this universal gas pool is deepest. The cosmic web is the framework, and the Lyman alpha forest is its shadow, a silhouette cast upon the light of ancient quasars, revealing the universe's hidden skeleton in lines of absorbed light. That cosmic web is a highway for particles of immense power, and their journey ends in the cold, dark places where chemistry begins. The constant, invisible rain of cosmic rays does far more than just scramble their own origins. It acts as a hidden chemist within molecular clouds, ionizing molecules and kickstarting chains of reactions that would otherwise lie dormant. A single cosmic ray proton screaming through the void can tear an electron from a hydrogen molecule as it passes. This creates a positively charged hydrogen ion, a highly reactive fragment that becomes a catalyst for change. It can donate its charge to other molecules like carbon monoxide or water, setting off a cascade. This ion molecule chemistry is a unique pathway, often leading to larger, more complex organic species much faster than the slow surface chemistry on dust grains. In the frigid depths of a cloud where thermal energy is almost non-existent, cosmic rays provide the essential spark. Without this persistent ionization, the rich molecular soup we detect, the alcohols, the sugars, the precursors to life, might never form. The mystery deepens when we try to measure the intensity of this cosmic spark. The cosmic ray ionization rate is not a universal constant. It appears to vary dramatically from one part of the galaxy to another, and we do not fully understand why. In some quiet, dark clouds, the rate is low, suggesting a relative calm. In others, particularly near recent supernova remnants or regions of intense star formation, the ionization rate can be orders of magnitude higher. Astronomers measure this rate by looking for the chemical fingerprints it leaves behind. Certain molecules, like deuterated hydrogen or specific ions of helium, act as cosmic dosimeters. Their abundance directly reflects how much ionizing radiation has flooded the cloud. Maps of these molecules reveal a patchwork galaxy where the chemical destiny of a stellar nursery is shaped by its exposure to this invisible radiation. To visualize this, picture the serene structure of a dark nebula like Barnard 68. Now animated with faint, streaking lines of light cosmic rays piercing the cloud from all directions. Where each line passes, a brief, localized web of chemical reactions ignites, represented by quick flashes of connection between molecular structures. A simple hydrogen molecule splits, its ion shooting off to collide with a carbon monoxide, forming a new reactive ion. This cascade continues, building complexity in microseconds, a silent fireworks display of creation at the atomic level. This variation in ionization rate is a critical puzzle. It means two otherwise identical clouds could produce completely different sets of molecules, simply because one lies nearer to a source of cosmic rays. This directly influences the initial chemical inventory of a forming planetary system. A protoplanetary disk born in a high-radiation environment might be seeded with a different suite of organic compounds than one born in a quiet suburb of the galaxy. The cosmic rays, those lost messengers from galactic accelerators, may therefore hold a second, quieter role as the variable pen that writes the opening chemical lines in the story of a new world. Their unknown flux becomes a hidden variable in the recipe for life itself. The cosmic rays that seed chemistry also illuminate the galaxy's darkest failures. Scattered throughout the molecular clouds we call stellar nurseries are dense, cold pockets of gas that have all the right ingredients for star birth, yet remain forever still. These are the starless cores, and their stubborn inactivity is a profound puzzle. They possess the mass, the density, and the frigid temperatures that should trigger gravitational collapse. By all accounts, they should be glowing with the first light of protostars. Instead, they linger in a state of suspended animation, dark and quiet against the infrared glow of their dusty surroundings. What invisible hand is holding back the force of gravity? The answer likely lies in the delicate balance of support mechanisms we have already encountered. A core's internal turbulence can provide enough chaotic pressure to prop it up, like a building made of swirling winds. More compelling is the power of magnetic fields. Imagine the core threaded with lines of magnetic force acting as a cosmic cage. These field lines resist the inward pull of gravity, effectively freezing the core in place. For collapse to begin, the gas must slowly slip across these field lines, a process called ambipolar diffusion, which can take millions of years longer than a simple free fall. This makes a starless core not a failure, but a patient clock ticking down toward an ignition that is simply not yet due. Their study is a direct window into the profound inefficiency of star formation. For every dense core that successfully forms a star, there are many more that dissipate or remain dormant. The galaxy is littered with these stillborn possibilities. The contrast in observations is stark. In a millimeter-wave telescope image of a cloud like Taurus, both types of cores appear as bright, compact knots against a fainter background. But point an infrared telescope at the same region, and the difference becomes cosmic. The protostellar cores blaze with the warmth of nascent suns, while the starless cores remain dark, absorbing the background light and appearing as Inkai silhouettes. They are the universe's paused projects, and by understanding why they have not yet pressed play, we learn the precise conditions that must align to turn a cloud of gas into a beacon of light. The cosmic stillness of those starless cores hints at a far greater silence waiting at the end of time. Every birth we have witnessed, every violent cycle of enrichment and destruction, is part of a grand one-way journey. The interstellar medium is not just a nursery or a recycling center. It is a finite reservoir, and we are watching it slowly drain. This is the ultimate mystery of its fate, a countdown clock for the galaxy's creative power. Over cosmic eons, more and more of the galaxy's raw hydrogen gas is converted into stars. Those stars, in turn, forge heavier elements and fling them back into the void, but the process is not perfectly efficient. A significant fraction of the original gas supply becomes permanently locked away. It ends its journey not as free-floating fuel, but as stellar corpses, white dwarfs, neutron stars, and black holes, or as long-lived, low-mass stars that will shine for trillions of years, hoarding their material. This slow exhaustion has a name: quenching. A quenched galaxy is one that has run out of the cold, dense gas necessary to form new stars. It becomes a cosmic retirement home, filled with aging red stars, its spiral arms fading into a smooth golden haze. We see such quenched galaxies in the universe today, massive ellipticals that seem to have concluded their star-forming eons ago. The mystery is not if it happens, but how and what forces accelerate the final act. Here, the galaxy's most destructive citizens take center stage. Supermassive black holes like the one at our own galactic center may play a paradoxical role. While their occasional outbursts can compress gas and trigger star formation locally, their larger-scale influence is one of breathtaking sterilization. When a black hole feeds, it can drive immense galactic winds, powerful outflows that scour a galaxy clean of its remaining gas. This wind does not gently recycle. It ejects material entirely, blowing it out into the intergalactic void where it may never fall back. It is a permanent loss. The effect is like a raging forest fire that not only burns the trees but also sterilizes the soil, preventing new growth for eons. Visualizing this final evolution requires a time-lapse on a billion-year scale. Watch a vibrant blue spiral galaxy, rich with dusty lanes and glowing pink star-forming regions. As time accelerates, note the supernova bubbles and black hole-driven winds not just stirring the pot, but actively throwing precious gas overboard. The blue hues of hot, young stars begin to fade, outnumbered by the yellow and red glow of aging stellar populations. The spiral structure, once sharp and defined by bright newborn clusters, softens and blurs. The galaxy's color shifts from blue to green and finally to a dull red as the last pockets of cold gas are consumed or expelled. The final scene is a smooth, red ellipsoid, a galaxy whose interstellar medium has been silenced. its remaining stars will slowly burn out one by one over trillions of years, their light fading into an eventual permanent darkness. This is the fate awaiting every galaxy, including our own Milky Way. The great cycle of star birth and death is a story with a final chapter. The interstellar medium, that ghostly sea of potential, is the protagonist of that story, and its gradual disappearance marks the end of an era of cosmic construction. We are living in the golden age of this cycle, surrounded by the evidence of both creation and the inevitable quiet to come. From the faint spin of a single atom to the violent arcs of galactic fountains, the interstellar medium is a universe within our universe. We have wandered through 25 of its deepest enigmas, each a doorway into a different layer of cosmic reality. These are not isolated curiosities. They are interconnected threads in a single grand tapestry. The same supernova that forges new dust also seeds the chemistry for life and carves the cavities that shape stellar birth. The magnetic fields that guide cosmic rays also sculpt the clouds where stars are born. The faintest radio whisper from primordial hydrogen may hold secrets of dark matter, while the gamma ray glow from our galaxy's heart records a black hole's ancient roar. This invisible ocean is the true protagonist of our cosmic story. It is the reservoir from which every star, every planet, and every one of us was drawn. Its mysteries are not mere academic puzzles. They are the keys to our own origin, from the carbon in our cells to the iron in our blood, and they foretell the ultimate fate of our galaxy as its star-forming fuel slowly runs dry. Solving them means reading the autobiography of the Milky Way, written in shadows, magnetic fields, and ghostly light. So now we turn the question to you. After this journey from the quantum to the galactic, which of these 25 mysteries captured your imagination the most? Was it the survival of complex molecules in stellar infernos, the silent patience of starless cores, or the colossal Fermi bubbles towering over the galaxy? Share your thoughts in the comments below. If you want to keep exploring the hidden architecture of reality, be sure to subscribe for more deep dives into the universe's greatest puzzles. And the next time you look up at the night sky, remember, the greatest wonders are not just the points of light you see, but the vast, invisible, and magnificent sea in which they all swim.